All right, so last time, and I hope you enjoyed the visualization lectures as much as I did, we talked about effective and non-effective visualizations, and in particular, what makes them effective. And the basics for that, of course, visual attributes or visual variables, which are the vocabulary of visualizations, so the basic building blocks that you have, which are size, shape, color, and so on. And we talked a little bit in more detail about color because it's usually overused, yeah, and used in the wrong way. So we discussed the rainbow color scale and so on. And finally, we discussed the design principles by Edward Tufte. So like you need to maximize the data-ink ratio. You need to reduce chart chunk. So nothing unnecessary should be in the chart. Then we discussed the lie factor, and we discussed scales. And this is basically everything you need to know about statistical graphs. Today will be about multidimensional data visualization. So everything, if you take a whole table, how you can visualize it. Yeah? And the second part, which will be probably the smaller part today, is about maps and text. Yeah? There's a lot more to tell about these two topics, but I thought I will just try to summarize and tell you the most important stuff about that. All right, so multidimensional data visualization. I'm sure you remember the Titanic data set that we discussed last week. So in the Titanic data set, every row is an item, which is a passenger here, and every column is an attribute or a feature. Yeah? We have sex, age, fare, and so on and so forth. This is considered as a multi-dimensional data set. And we talked a lot about how to visualize it. If you just take one dimension, yeah, just taking one column, then you could show it as a histogram. If you take a second dimension, two columns, then you can show the correlation in a scatterplot. If you take the third column, we talked about the choices that you have. So three-dimensional visualizations is not really the way to go. The alternative that you could do is just make a 2D scatterplot and use a different visual variable, like color, to encode the third dimension. But this is the limitation here. So what would be the natural fourth dimension? Yeah? We have a three-dimensional world. We have two-dimensional displays. So how could we, if we take just 4 dimensions, how could we visualize that? Yeah? And as we said, the options are that for every dimension that you take, you just pick a different visual variable. So for instance, for the first 2 dimensions, you make a scatterplot out of it. Then you choose color for the third, shape for the fourth, size for the fifth, and so on and so forth. But of course, this gets harder to interpret. Yeah? It's a cognitively demanding task. So what alternatives do we have? And this will be probably the next 30 minutes. So first, I want to introduce what high-dimensional data is. Yeah? People talk about high-dimensional or multivariate data all the time. Yeah? For visualization, you need to think about these aspects. Can I use just visualization, or do I need to, in addition, use analytics for it? Yeah? And for instance, if you talk about dimensions or attributes, so the columns in the table, then if we just take up to 50, that's probably tractable with just visualization. But everything that is above needs to be combined with analytics before that, and then, in the end, visualization again. In terms of the items, we scale a little bit better in visualization. So about 1,000 is probably just fine with using visualization. But everything which is above, like 10,000 items, you need analytical methods. And you need to reduce the dimensionality of your data set. And this is what Raphael will talk about on Thursday. OK, if you have a high-dimensional data set, so a large table, you first need to look at the characteristics of the table. So is it homogeneous? Homogeneous means, are there different data types in the dimensions? Yeah? If this is mixed, like in the Titanic data set, then it's much harder to visualize than if it's homogeneous. Yeah? A homogeneous example would be a gene expression table, where you have thousands of columns, which are the genes, and the experiments or patients as rows. Yeah? This is a homogeneous data set because you can just pick one visualization technique to summarize this data set. But if you have heterogeneous data, so different types of data in the columns, then this is more difficult. Yeah? And this is the first thing you need to check about your data set. And then also important are scales, and we discussed that several times now. Even if you have a homogeneous data set, like a gene expression data set, it could be the case that the data in the dimensions are not directly comparable. For instance, that you need to normalize them to make them comparable. And this is also very important, to bring them to the same base or to the same range. Okay, so I'm going to introduce these different techniques that we have in visualization. And I will start with parallel coordinates and scatterplot matrices. And these are really powerful techniques that don't need much analytics. So you could, of course, use simple analytics to optimize, for instance, the order of the columns here or the order of the plots in the scatterplot matrix. Yeah? Then we will discuss heat maps. I'm supposed to use the mouse pointer for the extension school students. Okay, then we will discuss heat maps, and heat maps, they only work if you cluster them. Yeah? And clustering means that you group rows and columns according to similarity. Yeah? And this is also what Raphael will introduce on Thursday. And dimensionality reduction. This is reducing the visualization part. Yeah? For instance, for PCA, to show the result, this is just, again, a 2D plot. Yeah? It's very simple. But you have analytics that reduces your dimensionality. All right. Let's start with the table lens. Yeah? If you take the table and you just replace every value that you have, every cell with a bar, then you get this result. Yeah? And this is, you can even do that in Microsoft Excel, for instance, and you can then sort one column. So you can sort your whole table according to one column. Yeah? So if we take this university ranking from last time, then you could just sort by one column. Then we introduced lineup. So lineup is similar, but you allow people to stack the different dimensions on top of each other to create this stacked bar plots. And this allows you then to, for instance, weight your different attributes, like what you have in a university ranking. Yeah? And you already have seen how we get this, how we read such a table to Python, and how we can visualize it to make it this this stacked bar representation. Okay, this is what you already know. We haven't talked about heat maps yet. Yeah? The concept of heat maps is very simple. So you treat each cell as a pixel, and you assign a color to it according to the value that you have. Yeah? So you have a color map, like 0 would be, let's say, in that case, blue, and the maximum would be red. Yeah? And it's very important that the meaning is derived from the order. Yeah? So a heat map only makes sense if the order has a meaning. Yeah? A natural meaning could be time. Yeah? If you have experiments that are sorted according to the time stamp when you have acquired them, then this is a natural meaning and a natural sorting. Yeah? But if you have, like in that case, a huge gene expression data set, then you need to run a clustering to actually make these patterns appear. Yeah? If you don't run a clustering on such a table and you show it as a heat map, it will just look like noise. Yeah? So if you have this data, then clustering gets really important, and you will learn about that on Thursday. Okay, so in terms of scalability, this is a really powerful technique to summarize your data without losing too much information. So probably the practical limitation is that you assign each value in your, or each cell in your table 1 pixel. Then you don't lose any information at all, and if it's nicely clustered, then you will see really good patterns in your data without losing any information. If you further increase your data set, then at some point you will not have enough pixels on your screen. Irrespective of which screen you use, you will run out of pixels. Yeah? And then what happens is that you assign multiple values in your data set to 1 pixel. And then it will just be a mix of these cells that will be assigned as a color to 1 pixel. Yeah? But even if this is the case, that's usually not a problem, because when it's clustered, similar values will be next to each other, so it's not a problem if your graphics card summarizes that to just 1 color or 1 pixel. Yeah? But this only works if you have a powerful clustering algorithm. And as I said, this is really good for homogeneous data. Yeah? So if your dimensions are all the same, but if your dimensions, like in the Titanic data set, are very, very different, then you cannot show it just as a heat map. Yeah? So this would be an example. It's a clustered heat map plus a dendrogram. A dendrogram is this hierarchy representation. It's nothing else as a tree. And the idea here is that you have a hierarchical clustering. So in hierarchical clustering, you start by assigning each, in that case, each column to one cluster, and then you merge the clusters that are most similar to each other. And you do that recursively. What you get is this tree representation, and this is called a dendrogram. And for instance, if you have gene expression, you can do that in both directions. Like you first cluster the columns according to similarity, and then you do the same for the rows. Yeah? If you set a cutoff value, that's the line called here, then you can change the granularity of the clusters that you have. Yeah? Like you see here, the white lines, that are the borders of the cluster. So everything that is in this subtree would be one cluster. Yeah? And in that case, we're using a hierarchical visualization approach. That means you have a table that has not a nice aspect ratio. Yeah? Because we have, in that case, it's 40 experiments, but we have over 20,000 rows. Yeah? To make that, to make it better to actually handle that, we use a simple approach that you just show this heat map as it is, but you allow users to actually pick one subset and make it bigger. So this is what the second level is here, and you again let the user pick a subset, which is then shown in full detail. Yeah? And this is called overview and detail. It's a very important principle in visualization. Okay, what to do if we have heterogeneous data? Yeah? And this is an example from a paper where you have like different groups of patients. Here it's cancer subtypes. And we have here 4 different groups of patients. But here, the important thing is that the rows, they have a different meaning. Yeah? So we have gene expression, we have copy number values, and we have mutations, which are very, very different biological concepts. Yeah? But here, it's assigned to the same colors, which is actually not a good idea. Yeah? Because people will try to read some patterns which are actually not there, because it's actually completely different data. You can't compare a copy number value to a mutation value. Yeah? So what is much better would be this representation here, where you clearly separate your homogeneous parts in the table. So this first part would be all the mutations. So the columns are the genes. And the second part would be clinical data, and the third part would be copy number status. And here we even use different colors to make it very clear that these are different biological concepts or different biological data. Okay, let's move on to parallel coordinates. Who of you have heard about parallel coordinates before? No one. Okay, that's surprising, because it's a really powerful concept to show multidimensional data. The idea is very, very simple. Yeah? Let's start with this example here that shows a scatterplot representation, and we just have 2 data items, A and B. Yeah? In a parallel coordinates plot, we draw these axes, X and Y, next to each other to be parallel. Then we add these data items. Yeah? This is just projecting the values to the axis. So we have A has a high X value and a low Y value. Yeah? And what we do then is we connect it by lines. And this is everything you need to know about parallel coordinates. If we look at the data set, it's much clearer, because sometimes it takes a while to wrap your head around it. So that's in visualization a quite famous data set. It's the cars data set. It's attributes of different car models from 1980. So we have miles per gallon, cylinders, horsepower, weight, and so on. And what you do in parallel coordinates is we take every column and show it as one axis here. So this would be miles per gallon, this would be cylinders, horsepower. That's the very same what you have in the data set, in the table. And then every car model, which is a row here, would be one polyline. As I said before, you add for one row, you add one line. And then you see nice correlations. If you check the values between these two axes, miles per gallon and cylinders, then you will see a pattern that is not surprising. So cars with lots of cylinders, they have a low range. And this is the correlation that you see here. It's very, very effective to show such kind of data. Okay, what could be the limitation? Yes, there's a question. Yes. So the question was, if you only see these correlations between the axes, is that the question? So if I would like to see the correlation between miles per gallon and year, I would have a problem. Is that correct? Yes. And that was actually my next question. So what's the limitations of such a representation? And that's the first representation. You can only compare, you can only see the correlation between axes that are adjacent to each other. What would be another limitation? Any ideas? How about many axes? How about many items? And there are natural limitations of parallel coordinates. The first one would be if we have a really high-dimensional data set where we have, like in this case, 500 axes, you will only see, basically you see nothing. You just see some axes and some scattering of data values, but this is too much. So parallel coordinates cannot really cope with lots of dimensions that are probably above 20, I would say. Another natural limitation is that if you have lots of items, and we already talked about that, you will get a cluttered display. So at some point, you will only see black. And this is a quite tiny data set. That's just, I would say, 500 items. But even with 500 items, it gets cluttered very quickly. What would be a way to solve this? And we already discussed that with scatterplots. Yes?
Well, I don't know about scatterplots, but I know when a lot of people do this on maps, they use opacity.
Yes. So that would be the most natural thing to do. You use opacity, and then, of course, the effect that you get is that outliers will disappear, and strong trends will be very visible. And there are techniques that try to preserve these outliers then, so that you again increase the opacity for outliers, which would be lost otherwise. Another way to cope with many items is use sampling. If you have a data set that is normally distributed, then you could just throw out, let's say, every second item that you have. And the overall pattern will still be the same or very, very similar. And that's called sampling. And there are also more sophisticated techniques of sampling that first look at the distribution and then throw out the values. You could also cluster the data. For instance, you could cluster lines that have the same slope. And you cluster them together and just show them as one line. That's also a very powerful way to actually deal with this item issue. Then we have this limitation that we discussed. You can only see the correlation between two axes. How could we solve that? If we have an interactive version of this plot, how could we let the user fix that? Yes, you can just use interaction, and the user can drag and drop the axis to actually show the different correlations. Here you would see miles per gallon to horsepower. Now you see miles per gallon to cylinders, and so on. But this really requires the user to use interaction. So the user needs to work with the visualization. Okay, another limitation. So you see it's powerful, but you have some limitations that you need to be aware of. Another limitation is ambiguity. So if you have, let's say, so this is the axis, this one, and you have two lines, so two items, line A and line B. And now you need to tell if line B actually is going in this direction or in that direction, because they share the same point on the axis. And you can't actually tell, because it's the same pixel, and it just splits the line into two lines. So again here, if we have line A and we follow line A, here we can't tell if line A is going in that direction or in that direction. So by just showing a static plot, you can actually not really read one single line. A solution would be to use interactive highlighting, to let users pick one line, which you just change the color or make it thicker or so, and then you will immediately see how this line progresses. Another solution would be to use curves, and standard libraries, they have this option that you can change the line style from straight lines to curves. So for instance, here you have then curve A, which is item A, and B, and you immediately see that curve A is going like this, and curve B is just a straight curve. Okay, the next powerful technique are scatterplot matrices. Who has seen that before? And that should be more people compared to parallel coordinates. Okay, only a few again. The idea is the following. So you have n dimensions. In that cars data set, for instance, if we have 5 columns of this car data set, then we have 5 dimensions. And if we have 5 dimensions, we have 5 square scatterplots. So what we do is we just take every dimension and put it as a matrix, so that we have every dimension as a column. So that would be dimension 1, dimension 2, 3, and 4. And we also put the same dimensions as the rows. So that would be dimension 1, dimension 2, dimension 3, dimension 4. What you get is a matrix of scatterplots. That's why it's called scatterplot matrix, or SPLOM. And the effect that you have is you can see every correlation in your data set. That's something that you can't see in the parallel coordinates without interaction. Here you don't need interaction. You just need to check out where your plot is that shows the correlation. Is there something odd that you see here? So could you reduce it to actually show the same amount of information to show your data set? Could you remove some of the plots? Yes?
It's symmetrical along the diagonal. All of the plots on the upper left-hand corner are the same, or correspond to plots on the lower right-hand corner, except they're flipped.
Exactly. So the plots that you have here are just the flipped versions of the plots that you have on the other side of the diagonal. So if you look at this plot and this plot, they're basically the same. If you have dimension A and B, then this is A versus B, and this is B versus A. It's just flipped. So what people do is, when they actually look at scatterplot matrices, they just remove one side, all plots that are on one side of the diagonal, because they're just showing the same data. You could throw them away and keep the same amount of information. And the diagonal is projecting, of course, the same dimension to itself, so A to A. and it doesn't give you a lot of information. So you could remove this as well. And what people do often in that case is to replace the plots along the diagonal with, for instance, the histograms that show you the distribution of this particular dimension. This also has a limited scalability. For if we have more than, let's say, 20 dimensions, of course, we need a lot of tiny plots, and at some point, it's not reasonable anymore. In terms of items, so how many dots we have in the plot, it scales better, of course, but you have the same limitations that you have in a scatter plot. At some point, it will get very crowded, and you need to increase the transparency, for instance, or you need to use sampling, so not showing every data item in your data set. All right, so as a summary, here we have a very simple table. This would be the scatterplot matrix encoding the table, and as you see, we have quite some plots. But it shows us every combination that you have in this table. Math versus physics, physics versus drama, and so on. This would be the parallel coordinates plot. And here you can see why I like it so much. It's a very simple encoding for this table. And it's very space efficient as well, if you compare it to the scatterplot matrix. But you have the limitations that we discussed a couple of minutes ago. That you need interaction to see all the different combinations and so on. Okay. There are really nice approaches. So people thought, in the InfoVis community, people thought about how can we generalize these concepts. So we have parallel coordinates and we have scatter plots. When you look at them, they are nothing else than just axes where you project the data onto it. So for instance, that would be an axis and that would be an axis. If you just rotate one axis by 90 degrees and you project the data, what you get is a scatter plot. And this guy, Jaak van Wijk, who is a professor from the Netherlands, and his PhD student, they proposed this flexible linked axis concept. And that's a prototype where you can really just add every dimension of your data set could be added as an axis. And if you drag them to be parallel to each other, they will be connected by lines. If you rotate one axis and you put it in a 90-degree angle to each other, then it will show these scatter plots here. And then you can, of course, create all kinds of combinations. For instance, you could arrange them in this star plot shape. You could just pick one axis, which is the most interesting for you in the center, and just put everything around that. And this concept is called flexible linked axis. It's just a generalization of simple scatter plots and parallel coordinates. Yes, there's a question?
What situation would you want to use a hyperbox over a scatter plot?
Where's a hyperbox? Yeah, that's just to show, I would say, to showcase what you can do with the technique. But of course, this is not a valid option. I think if I remember the paper correctly, what the authors tried to do is they reproduced some plots that were published before, that have been published before. So they just showed that their concept actually covers everything what was published before in that direction. But I'm not arguing with you that this is an effective representation. Okay, and yeah, if you want to try it, there's a really nice web-based prototype where you can just load your own data set, load everything as one axis and try to play around with it. Okay, then, so these are now non-standard techniques, but I just want to show you what people are trying in that direction. So what you have here are simple plots. And when you have simple plots and you have multiple of them, it's sometimes hard to see how what's the relation between them. And in connected charts, McGuffin, so that's a Canadian professor, he suggested to add on demand, to add these lines that actually show how they belong together. So here you see you have a twist here between these two, between this plot and that plot here. So the order of dimensions is actually switched. And this is a really nice technique that we did together, so that my PhD student did together with Hans-Peter Pfister at SIAS. And I want to show you a video. Everything is based on simple statistical plots. Yeah? But the technique allows you to arrange them and to create these visualizations on the fly according to your preferences. Yeah? And I will show you a video very quick. And this, of course, goes beyond simple static plots because it requires user to interact with the data. So the technique is called Domino. And what you have is a domino board, which is just a blank space that you have, and a browser where you have all your dimensions loaded, actually. We have 3 different types of blocks in Domino, which is that you can handle different kinds of data. We have partitioned blocks, which show you categorical data. Yeah? In that case, it's a music data set, and we have loaded like 20 different musicians, and we show if the musician is female, male, or a group. Yeah? So that's partitioned. Then we have numerical. So numerical can be shown as this bar plot. And the third type is a matrix. In that case, it's the number 1 hits of these artists in the different countries. Yeah? Okay. Now, what we can do here is, or the user, if you put them next to each other, they will immediately connect it using these lines. Yeah? And you have a concept that we call placeholders. So you just drag the data set from the list that you have there, and you can pick the representation. Yeah? For instance, here we load the different, we load the origin of these groups. So if they're from the US, and you can see that most of the males are from the US. Then we say we want to see the number 1 hits of these artists. So we just drag the table into there. And that's like an interactive version to create your own plots. And you can customize for every part, you can customize what you want to do. For instance, here, I want to see it as an axis. If I want to see it as an axis, what I get is immediately a parallel coordinates plot. Yeah? If I just rotate this axis, what I get is a scatter plot. Yeah? So that's a really intuitive way to handle your data. You just pick the dimension that you have, add it to the board, and then you can interactively create whatever you want. Okay. Yeah, another thing you could do is radial axis techniques. It's similar to parallel coordinate plots, and it just arranges the axis that you have in this. Yeah, the axis radiate from a common origin. Yeah? And they're all different versions that you could create, but the most widely used are star plots. Yeah? And if you look at newspapers, sometimes they use it. What you have here is that you have each axis here, and they share a common origin. Yeah? And instead of showing them in parallel to each other, you just arrange them in this star fashion. Yeah? And what you do then is you connect the values across the different axes, and then you get different shapes. If we do that for a cars data set, for instance, then every car would result in a different shape. Yeah? And if you're used to work with such a system, then you will immediately recognize what's the shape of the different cars and what the associated values are. Yeah? And these are called star plots. It's a technique that is pretty old, so you see it was proposed in 1969. Yeah, there are more absurd versions called the Chernoff phases. Yeah? And the Chernoff phases, they try to encode your data in different visual attributes that are shown as different phases. Yeah? For instance, you assign one column in your data to the size of the face. You assign one column in the data to the position of the eyes, to the length of the nose, to the position of the mouth. Yeah? And this will result in different faces for every different item that you have. Yeah? And I don't think that this is effective. Yeah? Don't get me wrong. This is actually a horrible technique to visualize your data, but it's just an option that you have. What makes more sense is to, so this does not work, by the way. What makes more sense is to use glyphs. Yeah? And glyphs, it's a more general technique than Chernoff faces. And in a glyph, you create tiny plots that encode your data. For instance, a tiny plot could be a bar plot, or it could be this face glyph, which we discussed. It's not that good. It could also be a tiny heat map. Yeah? And this is called a glyph, or an icon. And there are different versions of this. If you create glyphs, and if you have users that use a system very often, then they will recognize these different glyphs. For instance, if you have different categories, like is it a molecule, cellular part, cell, tissue, organ, and so on, instead of using color, you actually create these glyphs. And if people remember these glyphs, then it's much more effective than just using a color. Because with color, if you have more than 6 to 10 different versions, you can't recognize the difference anymore. And the example on the left is actually, you have a multidimensional data set, and you encode the different dimensions in different properties of this little guy here. For instance, you have, oh, this is German labels, that's interesting. You have different caps here. If it's black, then the patient already died. Then here you have the height is how long the patient is free of disease, and so on. And you have different colors here that shows the tumor staging. Yeah? And if you arrange these little glyphs in a scatterplot fashion, then you can read much more than just 2 properties. Yeah? And these are called glyphs. If you use these glyphs as marks in scatterplots, then this is a valid option that you have. Yeah? So for instance, here you have 2 different attributes, 2 different columns. It's proline and color in that case. And you create a scatterplot, and instead of just showing 1 dot, you create these glyphs. Yeah? And these glyphs look very different, and they can encode 4 different dimensions. So alcohol, phenols, and so on. Yeah? And if you see the different shapes, yeah, for instance, this guy is similar to that guy, but very different from that guy here. Yeah? And this is easy to recognize for you. But the basic choice that you have is you could create one single complex visualization, yeah, like parallel coordinates, or you can stick with your simple plots, like scatter plots, and just arrange them in a different fashion. Yeah? For instance, and this is called multiple simple visualizations. Yeah? And if you have a multidimensional data set, it's always this choice if you just stick with your primitive statistical graphs, or you go with something like parallel coordinates or something like a heat map. Yeah? Okay, so in the second part, I will talk about maps and text visualization. Okay, when we have maps, so you see maps all the time, yeah, and people project data onto the maps. That's what you see in newspapers, yeah, and this is widely used, and that's why I want to mention it. Yeah, for a lot of data that you have, even if you have a baseball data set, of course you can also project it directly onto a map and look at the distribution between east and west or whatever. Yeah? When you work with maps, you always need to think about the projection. Yeah? And you maybe know that from school that you have different projections, like you have a cylindrical projection, you could have a plane projection, which would be this here, or you could have a cone projection. And yeah, here would be an overview of different projections. But I want to show you that projections are so important because they completely distort your data. Yeah? If you take the same picture and you just show it using the different projections, then you will see the distortions, the distortion effects that you get. Yeah? Because our world is a sphere. Yeah? What we need to do when we get it to a two-dimensional display is called projection. Yeah? And if we project it to this regular grid here, what happens is that we get really huge distortions in the lower part and in the upper part. Yeah? And yeah, there are different ways to project this, and there is a nice web demo showing all different map projections like mole weight and so on. And the grid actually tells you how much the distortion in every part is. Yeah? The closer the grid lines are together, the more distorted your data set gets. Okay, and this is actually, it's the same demo, but it combines the parallel coordinates plot that I've shown before and these projections. Yeah? What you have here are these most widely used projections, and you have different parameters of these projections, like is it aerial, how much, what's the angular part here, and this is the brushing that I've told you before. Yeah? If you let the user select this little line here, it's easy to actually follow the same item through the different axes or through the different dimensions. Okay, so when we project data onto maps, then we have the visual variables that we learned about last time. Yeah, we have size, shape, brightness, color, the basic choices. What's missing here? What visual variable is missing? There's one important variable missing, which we can't use. It's the position. Yeah? Last time we discussed that position is actually the most effective way of encoding data, irrespective of the data type. Yeah? Why is it missing if we talk about maps? It's a very simple reason, actually. Yeah, because position is already used by the encoding of the map. Yeah? If we want to encode some data on a map and we see the data point which is representing Boston, yeah? And then we make it bigger according to the effect that we have in Boston, then you can't change the position because you would move the actual city. Yeah? That's why we can't use position with maps. Yeah, a very simple way is the dot map. Yeah? For instance, you count all accidents that happen in the US and you draw a dot there. Yeah? And you could change the color of the dot to I don't know, encode the different types of accidents. Yeah? And the limitation here is actually with dot maps, it's a little bit tricky because when you look at dot maps, they will always just show you the distribution of the amount or of the number of items that you have. Yeah? If you look at accidents and you project the accidents across the whole country, it will always just look like the distribution of the map. Yeah? So if we look at the US by night, then you will see a lot of people are living here. Yeah? We have this bright light dots here. And irrespective of which data you collect, it will always just show you the distribution or the population on the map. Yeah? So there is this really nice XKCD comic. It's saying geographic profile maps, which are basically just population maps. Yeah? So you could show someone 3 different maps. You could say there is a pattern between these 3 variables. So that's our site users, that are subscribers to Martha Stewart Living, and that's consumers of furry pornography. And the business implications are clear. Yeah? Because they just show the same, and people would assume that there is a correlation between that. Yeah? But there is no correlation. It's just a population map. Yeah? In densely populated regions, you will have more dots, and if you show it as a density map, it will be more intense. Like here, it would get red. Yeah? But this is just a population map. It doesn't tell you anything about the data. Yeah? And that's another way to lie with maps. Yeah? And if people are not trained to identify such things, then you can tell them basically everything what you want. Yeah? Okay, there is, Microsoft Excel 2013. It actually allows you to do some, I would say, fancy visualization. Yeah, and you can do really strange stuff. Like for instance, you could map some values to the height of these bars here. And here we have the same problems as we've discussed last time. We have occlusion, so we can't see what's going on here actually because the tall bars are hiding the bars that are behind that. Another problem is we could create a plot with, I don't know, 20 or 30 different colors, which you need to assign then to the different colors in the bar, to the different colors in the bars, yeah? Which is impossible. Yeah? So the important message here is you can always do stuff that looks fancy, but you really need to think about what you are actually visualizing, because the application or the software will not prevent you from doing bad things. Yeah? Even if, of course, Microsoft, they have guys that know how to visualize data. Okay, the probably most prominent way how to visualize or how to encode data on a map is the choropleth map. Yeah? And it just takes the attribute from your data set and it uniformly distributes it in a region. Yeah? So if we have the different parts here, these are uniformly colored according to the value in your data set. But there is a problem with that too. So choropleth maps can be misleading, yeah? Because the visual impact or the visual impression that you get can be wrong. Yeah? For instance, here this is Obama versus Romney, I guess. And you have them Democrats and Republicans. Yeah? And the Democrats, they have 330, and the Democrats have 206. So the number here is much higher. But when you look at the actual map, you will get the impression that the Republicans are doing better than the Democrats. Yeah? So you actually get the wrong impression here. What's the reason why you get the wrong impression? So it tells the wrong story, this picture. Yes, the size of the states does not correlate or is not related to the actual number of voters in that state. Yeah? So for instance, in Texas, Texas is not very densely populated, yeah? But it has a really huge visual impact because it's so huge. And you just uniformly color Texas as Republican. And the same happens here. Yeah? If you have highly densely populated regions, then these will be very tiny and they will not contribute much to the overall image. And so this was the version in the Huffington Post. And the New York Times, as I said, they really have a great graphics department. They hired some of the best people in our field. They actually made it better. So they just changed the size of this dot according to the population that you have in that part of the country. So you have lots of people living here in LA. You have lots of people living in New York, Boston, and so. So they should really contribute more to the visual impact of this figure. Yeah? And here in Texas, the dots are very tiny, very small, because only a few people live there. Yeah? I mean, compared to other parts of the country. No offense. So this is actually more effective. Yeah? And the reason is that choropleth maps, they also can be used to tell the wrong story. Then we have isarithmic maps. Yeah? Isarithmic maps are different because they take a continuous phenomenon and they color code it on top of a map. Yeah? So it's independent of the borders that we have here. It's just a continuous effect, like what's the weather, what's the temperature in the different parts of the country. And that's called an isarithmic map. Yeah? You, of course, you don't want to encode the weather in a choropleth map. In that case, it's not the weather, it's also the evolution of political parties in the US. So you see 1944, 1940, so it's actually moving backwards now. 1936, it was all Democrats and so on. This is called an isorhythmic map. Okay, then there is a really interesting option that we have. It's called cartograms. Yeah, and cartograms, they just scale the region. If we take the states as separate regions, then we could make them tinier or larger according to, for instance, the number of people that live there, to decrease the visual impact of, again, Texas, and to increase the visual impact of New York or so. There are non-continuous cartograms, so where you actually just make them smaller or bigger. A circular cartogram would be to take circles and replace the whole map by just circles. And of course, this only makes sense to tell the user the rough numbers, but you completely lose the relation to the geography behind it, of course. And the most widely used cartograms are these continuous cartograms. What's done here is that you just decrease the size according to a parameter and increase, for instance, here, if you have lots of population, you increase the size here. So these states are actually getting much bigger than they actually are. And these states here are getting smaller and smaller. Yeah? And that would be the interactive version. If you look at the data set here and you make the states bigger and smaller according to the data that you have there, then this is called a cartogram. Yeah? And you will probably see that sometimes. Of course, it distorts the geographical position of the states, but sometimes this is not important, because people know where Texas is, people know where California is. So you can actually try to distort that a little bit to make the visual impact more correct, actually. Okay. So if you want to encode connections on a map, like what you have if you want to encode flight connections, or you want to encode, in that case, it's migration data in the US. So who migrates from which part of the country to which other part of the country. Then if you just add lines, it will get really cluttered. So you can't see any trends. And there is a quite powerful technique, it's called edge bundling. You add forces between the different lines to form these bundles. And at some point, these bundles will show you the main trends. For instance, if you look at California, lots of people are moving, probably these are the snowbirds moving to Florida. Then you have some people moving to the East Coast, and so on. And this is a very effective way to show line connections, to show connection data onto a map. And this is, of course, also a very old technique. It's called flow maps. So flow maps, this is again a figure, a graphics created by Minard, so Napoleon's map maker. And we had this example with the march towards Moscow. And this is just a different visualization that he created. It's also a very early example of a really effective plot. So you see the wine export from France to other parts of the world. Okay, now in the last part for today, I want to talk about text visualization. And in text visualization, the simplest way how we can represent text is to just show the number. That would be the US public debt that I downloaded, or that I looked up yesterday on this. There's a counter website which is counting incredibly fast, actually. And that would be a very simple way to visualize text. But of course, if you scrape the web, for example, there's an API to access Twitter data, to access all the tweets live. But if you want to process them and visualize them, then you need to find a way to do that. And this is why we need text visualization. Probably the most prominent way to do that are tag clouds or word clouds, Wordle. There are different names for the same thing. The idea is that we change the word according to the frequency in the text. Yeah? The more often it appears, the bigger it will be in the graphic. So what we have here is it compares the state of the Union address from 2002 versus 2011. Yeah? And this was President Bush, and this is President Obama. Yeah? And the bigger the word is, the more often it was used in the speech. Yeah? So Obama was talking a lot about people, jobs, American business, work, yeah? And there you see a pattern. Yeah? That was the major theme in 2011 in his speech. And Bush was talking about world, weapons, terrorists, security, nation, freedom, and so on. Yeah? So there was really a difference in the semantics of these speeches. Yeah? And this is nicely demonstrated here. So if we have really large amount of text, you could just try to communicate the message in one tiny graphics. Yeah? And this is called the tag cloud, word cloud. And there's a nice website where you can just enter a URL, and it will take all the text from this URL, and it will create you this word cloud. And you can then also change parameters like what should be the angles of the word, what kind of colors do I want to use, what kind of font style do I want to use, and so on. And this is, so if you look at blocks, there are many different block frameworks. They have this nice plugin where you can just add a tiny word cloud showing the main themes in your blog posts. Yeah? And that's a really cool way to summarize text. Then there are spark clouds. So spark clouds, they can be used to convey actually trends over time. So if you have multiple tag clouds, and you want to tell the user what are the patterns over time. Yeah? And this, of course, changes. If you have some kind of newspaper, of course, the main themes will change. Yeah? And here you just add a tiny plot showing the frequency of this word over time. Yeah? So time is progressing on the x-axis, and the higher it is, the higher the frequency is. Yeah? It's a very simple concept. And this is called spark clouds. And it was a paper a while ago published by Microsoft. Yeah, a nice example is also PhraseNet. Yeah? PhraseNets are tiny graph representations, and these graphs, they show you different connections, semantic or lexical connections in your text data set. Yeah? For instance, in that example, they took the relations in 18th and 19th century novels. So they took all novels, took the text and analyzed the text, and tried to find out the relations between the different entities or the different people in the novels. And there you have then interesting connections. For instance, the wife is connected to the father, it's connected to the ambassador, to the officer, and so on, which completely makes sense. But the bride is connected to the freebooter, to the bandit, to the outlaw, to the sailor, to the pirate, which also makes sense. And the more frequent the word is, the bigger the word is. Yeah? So here you can, again, just create one tiny visualization that actually could summarize millions of different words or thousands of different documents. Yeah? Okay, there's also, so we talked about these stacked bar graphs, and this is just a different version of it. It's called theme river or stream graph. The idea is that you have different topics. Yeah? In text, it's always important to know the different themes, for instance. Or this example would be the films from summer 2007. Yeah? And there you see, so time is progressing from top to bottom. And the thicker the stream is, the more people went to watch the movie. So we had Shrek, and at the beginning, it's always quite popular. and then it gets less and less, of course. And then it results in these nice patterns that you have here. Another version, so it's published by Wattenberg here, is the baby name Voyager. That's also a stream graph. And there you just calculate how many of the newborns were given a particular name. If I go to this baby name wizard website, and this guy now, so Wattenberg, he moved to work for Google now some years ago. So if you go to, for instance, Google Analytics, then you will see what impact these guys have at Microsoft, at Google. So name Voyager, if we go here, then we have all different names. For instance, we could now filter for boys. We see James was quite popular in the 30s, and then it got less and less. And now if I look for my name, Mark, there you see a peak. There was a peak in the 1950s and 60s, but the name was really getting less and less popular in recent years. So I was born in '83, and it was again, or it was already not so popular anymore. So this is a stream graph. And here are some examples that I really like a lot in text visualization. And this particular example is about summarizing some features in books. And it's called literature fingerprinting. The idea is that, for instance, here every book is one heat map. So we have books written by Jack London and books written by Mark Twain. If you look at, in that case, the color, so every block here, every tiny block is a text block, every cell of the heat map, and every group is a book, as I said, and the color is the average sentence length. This is something, it's of course very easy to calculate. You just need to read in all the sentences, count the number of, or the length of the string, and encode it to these, or map it to this color map here. Sure. So short sentences are red, and long sentences are blue, and neutral length, so average length sentences are neutral, white. When we look at the books now, there are really interesting patterns. For instance, Mark Twain, he used to use medium length or long sentences. But at some point, it completely, the pattern switches, and no one knows why. And this, of course, raises some interesting questions. So maybe there was a ghostwriter involved, or so it's very unusual that a person or an author changes the style of writing completely. After years of writing, at some point you choose to write shorter sentences. That doesn't really make sense. And in Tom Sawyer, there are really short sentences if you look at it. And that's a really cool way to summarize documents or summarize large amounts of text. This is another example. It's readability analysis by the same lab. So it's a German lab from Konstanz. And this is, again, the goal is to create these fingerprints showing the different features of text. For instance, here there is an average readability score, so how easy it is to read the text. And this depends on several features, like how difficult are the vocabulary, or how long is the average length of the words, or what's the complexity of the sentence structure. And if you merge them together, then you get this readability score. And these measures are actually also a nice way to find, for instance, to identify plagiarism. If you have a thesis and you just use very simple text analysis and you create these plots here, if you have a switch in the pattern, then it's a very strong pointer that there's something wrong with this particular part of a thesis or a book or so. So it's a really great way to identify pieces that have been copied from other sources. Yeah, this is probably a little bit off topic, but I like it so much that I want to show it to you. It's now the other way around. You take text and you want to create graphics out of it. Yeah? And that's a project. So it was a SIGGRAPH paper, so the major graphics conference from 2001. And you actually take a piece of text and you try to create a visual representation or a computer graphics scene that shows what's going on in the text. Yeah? So for instance, this text would be the lawnmower is 5 feet tall. Yeah? So you add the lawnmower to the scene. Then you say John pushes the lawnmower. This is John, but it's underspecified because no one wrote what's the relation between the lawnmower, the size of the lawnmower, and this guy pushing it. Yeah? So this is underspecified. So that's actually wrong then. And then the cat is 5 feet behind John. And the cat is 10 feet tall. This is the cat here. And there's a great, so they actually try to make a product out of this, and they are launching this as a company. It's called Bird's Eye. And if you go to this to their website, they have these little text pieces, and they created this system that just tries to create the computer graphics scene out of it, which is really funny, I think. Okay, this would be the last topic for today that I want to mention. It's actually very, very short. If you're looking for software that is ready to use to interactively analyze your data, so there is no coding involved, there's just, you need to learn how to use the software, and then you can create quite effective visualizations. And there is a great software, it's called Tableau, and this is actually one of the fastest growing companies in the US. It was founded a couple of years ago, and they already have 1,500 employees. And everything started with so Pat Hanrahan is a professor at Stanford, and he and his PhD student, they actually created this company Tableau. And Tableau is, they have, so you can go there, try the software, and there's also a public software which has the same feature set, but it's just limited to the size of the data that you use. So they have only a limitation in the size, otherwise it's the same feature set. And there you really see what's the state of the art in terms of visualization of commercial products that you can buy. Of course, there are many more other companies that try to sell that. If you want to create your own interactive visualization, so that's different to what you can do with Matplotlib, which is also very effective to create static plots in combination with Python. But if you want to create interactive plots and you want to try that, then you should really go for data-driven documents, D3, which is a JavaScript library, which is really hot nowadays. So everyone is using it. For instance, New York Times, the graphics department, their stuff is based on D3. It's a JavaScript library, as I said. It uses CSS 3, HTML5, and SVGs. And it's amazing how well it's documented. There are lots of examples out there, tutorials, free books, and this is the direction where you can expect a lot more. So many people are starting to use D3 now. Okay, so on Thursday, it will be about, the first part will be held by myself. It's about big data visualization, so how visualization tries to cope with what's considered as really big nowadays. And there are some concepts like aggregation, like filtering, like focus and context that I want to show you before Raphael is taking over. And as a last part for the visualization lectures, I'm going to introduce briefly a case study based on cancer data where you can see what you can do with more than just simple plots. If you have a system that is heavily customized to solve a hard problem, like analyzing cancer data, and then trying to create an interactive visualization. Yeah, and after that, Raphael is going to introduce the concept of distance. So if you want to cluster your data, you want to find groups, then distance is very important. So what makes them similar, basically. And then the last part will be about dimensionality reduction. So how can you use analytical techniques like principal component analysis will be very important to actually reduce the number of dimensions in your data set to a much lower size, which should give you the same patterns. Yeah? Of course, you lose some data, but the major trends and patterns should remain the same. Yeah? That's the main theme in dimensionality reduction. Okay, that's it for today. Are there any questions? It's a little bit shorter today, I guess you... Okay then, thank you for listening. See you on Thursday.